we'll go ahead and get started for today. Just before we get started for today, any questions? Down to our third last class at this point, so not much time left. So last day we talked about induction, we talked about Faraday's law and Lenz's law. Those two things go together to tell us about how we get induced potentials and fields and currents in circuits. So we'll do sort of the most typical example next, the most common one. So the one we'll look at, these are often just called slider problems. So we have a rail that's conducting, that's this bit right here. And we have a bar across the top, and that bar is free to move. We're going to move that in the magnetic field, and we're going to think about all the induced fields and potentials as we go. So our magnetic field is represented by these X's that points into the page. Our wire here, our slider, it's got a length L, and we're going to move it to the right with velocity V. So we'll think for a moment, and we're going to find this force in part C. If we're moving it to the right, then we have to pull on it, right? So we're exerting a force to make it move to the right. Typically, we're asked to find induced potential and current. Current, of course, will include the direction of current. To do this, we'll think about the direction of the induced field. We'll also find the induced magnetic force on this slider bar, put that in context of magnetic braking, and then we'll see how hard did we have to pull it to make it slide. So let's think about what happens in the problem. We're taking our slider, and we're going to assume that these rails are much longer. They just go on for a while. We're going to take our slider, and we're going to pull it to the right. That means we're changing the magnetic flux, because that's B times area. So we pull the slider to the right. Change magnetic flux. So if we change the magnetic flux, we are going to induce a magnetic field. What would the direction of the induced magnetic field be? So here's where we think about Lenz's law. Whenever we change a magnetic field, a new field will always be induced to oppose that change. Anybody want to take a stab at the direction of the induced field? Pulling this to the right. Sort of see the cogs turning, but nobody wants to commit. That's fine. So you can think about this practically just in terms of the number of X's into the page. So the X represents a B into the page. If we pull this to the right, we're going to have an area with more X's into the page. We've increased the number of magnetic field lines into the page. To oppose that, we have to induce some field out of the page to go against the ones that we've created into the page. We want to cancel those. So we induce B out of page. So we can draw those magnetic fields, and in general it's a good idea to draw them. So our induced field is going to be out of the page. And we're talking about the induced field inside of the loop. When we induce a field out of the page, we induce a current. To get the direction of the current, we apply our right-hand rule. So I'm going to imagine grabbing this lower part of the wire. I want to make a circle with my fingers that represents the magnetic field. So my knuckles right here have to come up out of the page. So my fingers have to point up because the magnetic field is out of the page at me. My thumb represents my current. So I see that my current is flowing to the right in this lower part of the wire. My current will come around the circuit this way. This direction would be clockwise in the circuit. So we induce a current clockwise, counterclockwise. Oh, I don't know why I have so much trouble with this. Counterclockwise. Yeah, counterclockwise. So we induce the current counterclockwise. Okay, so we didn't really answer part A, but here's our thought process for writing all of these things down. Now let's go through the steps of trying to figure out what is the induced potential and what is the induced current. So from Faraday's law, we know that induced potential, and we're going to start, let's just find the magnitude, is minus d phi dt. We know that the negative sign implies that the potential is induced in such a way as to oppose the change. So it's okay if we just want to find the magnitude of the induced potential, because the direction of our current takes care of the negative sign. So if we want to find this, we're going to need what is our change in flux. Our magnetic flux, phi b, is the magnetic field dotted with the area, equals b times area times cosine of 0. So the field is out of the page, the area is out of the page, those two things are parallel, so the angle is 0 degrees. So we've got b times a. A refers to the area of the loop. So we've got a length here that we've labeled L. And then in the horizontal direction, we can label that W for width. So area is length times width. For our induced potential, we know we need the derivative, d phi dt. So let's find that bit as well. So we're going to do the derivative, d by dt, of field times length times width. Let's think about what the constants are. The magnetic field doesn't change, so that's our constant field. That comes out front of the integral. The length of this slide wire does not change. That comes out front. We're left with d by dt of this width. This width does change. We're pulling the slider to the right. That w is increasing. Change in position over change in time, that's just the velocity. So that width increases at a rate equal to the speed. Equals b times L times v. So now we can come back to our expression for our potential. The magnitude of the potential is going to be the magnitude of negative dLV, or just b times L times v. This is a result that's going to keep popping up, so this one occurs fairly often. And even though it pops up pretty often, you would still go through the steps of showing where that comes from. So if you're given a slider problem, you do need to show these steps to figure out what the potential is. So that's the induced potential. The induced current, we'll use our Ohm's law. So we know V equals IR. So to get our induced current, that's going to be the potential divided by the resistance. V times L times V divided by the resistance R. If this were a problem with numbers, we would pop in the numbers now and we would calculate the magnitude of that current. So that's part A done. Part B, find the induced magnetic force. So let's take stock of what we have now. We've got this wire moving to the right in a magnetic field. We've got a current going around the circuit. So we've got a current carrying wire in a magnetic field. It will experience a magnetic force. So part B, there's our slider. It's carrying current I. And it's in a magnetic field that points into the page. So the magnetic force that it feels equals I times L crossed with the magnetic field B. Let's use the right-hand rule to get the direction of the force. So our thumb goes in the direction of the current or the length. Those have the same direction. Our index finger goes in the direction of the magnetic field B, so it points into the page. Our extended middle finger shows us the direction of the force that points to the left. So IL cross B gives our force F. So that magnetic force is going to push this way. So the magnitude of the magnetic force is I times L times B times the sine of the angle between L and B, that's 90 degrees, equals ILB. But we remember, we just found our current, so we can fill this in our equation. BLV over R times L times B gives us B squared times L squared times V divided by the resistance R. That's our magnetic force. It points to the left, so we can call that the negative x direction, or negative I hat. Or I suppose you could just write the word to the left. Okay, so there's the induced magnetic force. What we see here, just like the demo I brought in last time, when we move this through the field, it experiences a force in the opposite direction. It slows it down. So this is kind of the heart of where all that magnetic braking comes from. So we get an induced current, and that acts to slow down the bar. So that's part B. I changed part C. I originally said find the power dissipated in the circuit. Instead, let's find the applied force on the slider. How hard do we have to pull it to get it to go to the right? So that'll be a Newton's second law analysis. So on our slider, where our current flows upwards, we know there's a magnetic force that points to the left. We also know it moves with constant velocity, okay, because that's the setup of the problem. It's moving to the right with constant velocity. So constant velocity means that the acceleration is equal to 0. If the acceleration is equal to 0, when we do our Newton's second law, the sum of the forces is mass times acceleration. It tells us that the net force is going to be 0. If there's a force slowing it down to the left, there must be a force pulling it to the right. That's us pulling on it. So we kind of established that it's moving to the right and we had to pull on it. So there's some force pulling it to the right. You can call that an applied force if you wish. So in our Newton's second law, we would have F applied minus FB is mass times the acceleration, which is 0 equals 0. So your applied force has to have the same magnitude and an opposite direction as the magnetic force. So we have to pull on it with an applied force of G squared L squared V over R to the right. So that will make it pull with constant velocity. Any questions? So let's think some more about that current flow and what's going on inside the bar. So let's sort of look kind of where that induced potential comes from, because that's going to lead us into our next little bit. So we've got a conducting bar. It's in a magnetic field. That magnetic field points into the page. We're going to pull the bar to the right, and then let's ask what happens because of that motion. So I'll put my velocity up here on the top. That's the direction of motion. So inside my bar, it's full of charges. Some of them are positive, some of them are negative. If we have these, the charges are in the bar is being pulled to the right. So the setup we have are charged particles moving in a magnetic field. We know they're going to feel a magnetic force. So the charges, both positive and negative, will feel a magnetic force. We know that magnetic force, FB, is equal to Q V cross B. So the magnitude of the force will be the charge times V times B times the sine of 90 degrees. And for the charges, we're talking about electrons and protons. So those are the charges inside the bar. The direction of the force, well, for my positive charges, V is this way, B is this way, the direction of the force points up. So V cross B gives the force. So the positive charges have a magnetic force that point up. And for our negative, we still do QV cross B, but where we have a negative charge, we have to rotate our answer by 180 degrees. For those charges, the magnetic force points down. So, if positive charges are pushed up and negative charges are pushed down, what it means is that all of the positive charge will drift to the top, and all of the negative charge will drift to the bottom. Okay, so the positives go up and the negatives go down. So the magnetic force results in positive charges move up, and negative charges move down. We've got the positives up here and the negatives down here. The charges have separated. If we think about what this looks like, that kind of looks like a capacitor, right? We've got one area of positive charge, one area of negative charge. This results in an electric field. So the electric field will point from the positive charge to the negative charge. We can draw our field in this picture if we wish. Picture is going to get a little bit messy, but that's okay. So there's our induced electric field, and this was induced because we've moved that bar in the magnetic field. So if we get an induced electric field, we also get an induced potential. We know that potential is electric field times the separation. So if I say that the length of my bar is L, then my potential would be the strength of that field times the length of the bar. So we definitely get the potential. If each of these charges are in equilibrium, and that's what will happen, is all of the charges will keep moving until the forces balance. Okay, so they will eventually reach an equilibrium. So in equilibrium, the magnetic force plus the electric force would sum to 0. So those charges would keep separating until the electric field got strong enough that it matched the magnetic force, and then they would stop moving because the net force on them would be 0. Our magnetic force is QV cross B, and our electric force is Q times E. Okay, this is kind of interesting. To me, this is really kind of neat. So this says that my electric field then, if I divide both sides by Q, is minus V cross B. So this tells us that we get an electric field induced just by the motion in a magnetic field. So a magnetic field can create an electric field. So that's kind of interesting. Okay, any questions here? So there's a link, yep.
Wouldn't there be an opposing magnetic field when the bars point to the right?
So if we had a conducting loop here, we would get that induced, yeah, so as the charges are moving, those moving charges will create a new magnetic field. That's true too, yeah, and we're kind of going there on the next slide, talking about how that happens. It's really nifty. So let's kind of talk about the meaning of those induced fields. So let's have our setup. We've got a magnetic field that points into the page. Those are the X's. And we have a loop sitting in the field. And let's say we have a conducting loop. That's supposed to be a good circle. I don't think it's exactly circular, but hopefully you get the idea. So here's our loop. It's sitting in a magnetic field that points into the page. Let's ask what happens when we change the magnetic field or change the magnetic flux. So if I increase B into the page, That means I'm changing the magnetic flux. We know that when I change a magnetic flux, I will always induce a new field to oppose the change. So if I've made B into the page bigger, to oppose that change, I will induce B out of the page. So I induce B out of page. For out of page, I'll write OOP. Induce B out of page. If I'm inducing a magnetic field out of the page, it induces a current in my loop. I'm imagining grabbing the bottom of the loop. My fingers come up to represent the magnetic field induced. My thumb goes to the right on the bottom. So the direction of my induced magnetic field, my induced current, will come on this way. Here's my induced current. Induce current counterclockwise. If I've induced a current, I've also induced a potential. So this is what we've done sort of for the last little while. That's what our first example was and some examples we did in last class. But we never asked the question, what made this potential? What made this current, right? It's kind of a good question. So what makes current or what makes potential is electric fields. Okay, so the reason those charges move to create this current is because there's an electric field. So what makes current and potential? The answer to that question is an induced electric field. We know that the current, the positive charges, move in the direction of the electric field. So the direction of the electric field is parallel to that current flow. So there's our induced electric field. So let's write down Faraday's law again, and then we'll add in this bit about the electric field. So Faraday's law said that our induced potential was minus d phi dt. And now we'll add the part that we know that the potential is related to the electric field because potential is the integral of E dot ds. So the integral of E dot ds is minus d by dt of magnetic field dotted with the area. This is actually kind of interesting, right? So this relates the electric and magnetic field like we did on the last slide, and it shows that a spatial change in electric field is related to a time change in magnetic field. So these two fields are not separable. They're tied together, right? If you have one, you have the other. They just don't exist separately. In chapter 20, so now this adds on a little bit to chapter 20. In chapter 20, we talked about electric fields being made by a source charge Q, you know, KQ over R squared and all that stuff. Well, this shows that there's another way to have an electric field, and you can induce it from a magnetic field. Those electric fields from source charges, those are called Coulomb fields because they exist due to charges with coulombs. These are called non-Coulomb fields. And the flip side of this exists too, right? You have magnetic fields around permanent magnets, and you can get magnetic fields from changing electric fields. So kind of two faces of the same coin. So Faraday said that a time change in magnetic field makes an electric field. Maxwell entered the party, and he said a time change in electric field makes a magnetic field. So he talked about it the same way, or talked about the same things. But what we see happening is that you change a magnetic field, you create an electric field that changes. You change that electric field, it makes a magnetic field that changes. That changing magnetic field makes an electric field that changes. That makes a B field that changes, an electric field that changes. It's completely circular, right? So they keep making fields that change each other. That led Maxwell to modify Ampere's law. So Ampere's law, we started out, we said that the integral of magnetic field over space, over a closed path, was mu naught times I. So that was our Ampere's law, and we use that to find the magnetic field in a solid cylinder and around a long wire and all that stuff. Maxwell added a term and said that it is this, but we also have to consider the fact if we change electric flux, we can also get that magnetic field. Okay, so Ampere did this bit, and Maxwell did this bit. This is one of 4 Maxwell's equations. If you go on to do Physics 3500, you'll talk about this a fair bit, and you'll do more about it, so this is just kind of a basic about it. What's neat about this is that this is a wave equation, so you've got a change in a field spatially related to a change in a field with time. That makes it a wave equation. This predicts that light is an electromagnetic wave with self-sustaining changing electric and magnetic fields. So each change induces a new change, which induces a change. So it just keeps going forever. And it predicts that the speed of light, so this led Maxwell to predict light is an EM wave with speed c equals 1 over mu naught epsilon naught square root. So Maxwell looked at this equation. I think that was around the 1820s. I think so. So Maxwell wrote this equation, thought about all this stuff, and he made this prediction. And then kind of Hertz came along in the late 1800s, and he made some radio waves, and he was able to measure the speed, and we saw that it was true. So I think that's kind of cool, right? You know, a mathematician writes this equation down, and all of a sudden is thinking about the nature of light and the universe. Like, I think that's pretty neat. So anyway, you'll do lots more about that in Physics 3500 if you go on to that. We'll leave it here. I don't think that we need to go more in depth, especially given that this is our third last class. But does anybody have any questions? Oh no, wait, I sort of would mention one more part. So we said there was a loop in this magnetic field, and then this ties into an example for last class. I said, what happens if we change the resistance of the loop? We said we'd still get the potential. If we still get the potential, we still have the field. So you might ask, do we even need the loop at all? And the answer would be no, right? This effect happens whether or not we put a loop here. It's just like if I hold a pen up in the air, it'll fall due to gravity, but if I put my pen away, gravity doesn't stop, right? Gravity is still there. These induced fields still exist, even if I don't have a loop. If I put a loop, the charges will move. If I don't have a loop, the field is still there, right? The fields don't go away. Okay, so that's the end of that stuff. Any questions? With this chapter, I posted a bunch of homework examples, and I kind of started looking at them, and I thought it might be a good idea for us to do a couple of those homework examples in class, just for some extra practice. So I won't do this one, magnetic flux through the loop. That one's pretty straightforward. I'll just put the answer up for that one. I'm not going to do this one because I'm not going to put that one on the test. So if you come across this one in your notes, look at it by all means if you're interested, but don't look for it on the exam because I won't put it there. The one I will start to go through will be this extra example because this is a pretty good question. It puts in a lot of details of the stuff we did about magnetic fields. So we'll look at this one. So this one is going to give us a nice review of most of the stuff we've done about our magnetic fields so far. So lots of details here in this problem. So a long straight wire carries current of 1 amp. That's this one right here. It shows that the current is flowing downwards. I've labeled that I1. And a nearby conducting loop carries a current of 2 amps, and I'm showing the flow of that current direction here. This edge of the loop is 1 centimeter away. It's 1 centimeter in width and 4 centimeters in length. So there's our setup. Now let's start going through the process of thinking about magnetic fields and forces. Part A, find the magnetic field at the left and right edges of the loop. So find the magnetic field here and find the magnetic field here. So to do this, we have to remember that magnetic fields make big circles around our wires. So our wire has a current flowing down. The magnetic field around the wire is going to make big circles. When we draw these circles, we put the wire at the center, and we put one rim of the circle where we're trying to find the field. We'd like to know the direction of the magnetic field right here at the left edge. Let's use our right-hand rule. I'm just going to turn my page around because that's kind of tricky to do with my hand. So I'm going to put my thumb in the direction of current. I'm asking what's the direction of my field right here. I see that my fingers are coming out of the page, so the direction of the field is out of the page. So the magnetic field direction at the left edge of the loop is out of the page. So part A, left edge. The size of the magnetic field, B on the left, is mu naught times the current. So when you're doing these problems, you got to be careful with your currents, right? This problem has two currents in it. We're trying to calculate the magnetic field at this position, and that magnetic field is created by this wire. So this is the field made by I1. That means when we're calculating the field, we use current I1. Those sorts of things, like they're small, but they're easy to get confused by. Then we have to divide it by 2 times pi times the distance between our wire and the left edge of the loop. Typically we use R. I'll put a subscript of L to remind us that we're talking about the left edge of the loop. We said the direction was out of the page. That'll be our plus K direction. We can put our numbers in here. 4 pi times 10 to the minus 7 Tesla meters over amps times I1, that's 1 amp, divided by 2 times pi times the distance from here to here, that's 1 centimeter, 0.01 meters. And the magnetic field at the left edge of the loop is equal to 2 times 10 to the minus 3 Teslas, and it points out of the page, so K hat. For our magnetic field at the right edge of the loop, same process. So we can do our circles again. So we want our circles to have the wire at the center and the right edge of the loop. Our direction, we find the same way. Current is our thumb, our extended fingers show the magnetic field. So everywhere on this side, the magnetic field points out of the page. So the magnetic field at the right edge, B on the right, mu naught times I1, remember I1 is the thing that's making the current, 2 pi times the distance between the wire and the right edge, call that R with an R on it. That's out of the page, so the plus K direction, put our numbers in. This time our distance is 2 centimeters. So at the right edge of the loop, our magnetic field is 1 times 10 to the minus 3 Teslas K. Okay, so wire 1 makes a magnetic field that points out of the page where the loop is, and there's the strength on either side. Questions there? So next, part B, find the magnetic force on the left and right edges of the loop. So our loop has current flowing through it, so that's a current carrying wire in a magnetic field. We know it'll feel a magnetic force. F is IL cross B. So let's look at the left and right edges of the loop. So part B, left edge. So the magnetic force equals IL cross B. let's be careful with our symbols here and make sure we understand what we're doing. This magnetic force is on the loop, the left edge of the loop, because it's sitting in the magnetic field made by the wire, so in shorthand, by the wire. Okay? So the wire makes a magnetic field, it sits in the field, this is the force on the loop. Because this is the force on the loop, we're using the current that flows through the loop, I2, and we're using the length of the loop. And our magnetic field is made by the wire. So when you're doing these equations, you have to be really careful about what makes what and which currents and which fields you have to put in, because they can get really tangly. So let's see what we have to put in here. Our I2 is our current, that's 2 amps. L2 is the length. It has a direction that matches the current direction. So the current flows up on the right, left on the top, down on the left. So there's our direction of our length and our current. It flows down, so the direction is going to be a negative j hat direction, and the length of it is 4 centimeters. Okay, so there's our length vector. That's crossed with the magnetic field it's sitting in, which was our 2 times 10 to the minus 3 Teslas K hat. If you wanted to do magnitude and direction, that's fine as well. So for magnitude and direction, you do IL cross B will give us our force that points towards the wire, and our math will make that work out as well. So this gives us minus 1.60 times 10 to the minus 4 j cross k. J cross k is I hat, so we get minus 1.60 times 10 to the minus 4 I hat, or to the left. So there's our magnetic force on the left part of the loop. Question? Okay, the right edge of the loop, that one will go faster. So we'll do the same thing again, except it's in a different magnetic field. On the right edge, FB equals I2L cross B. This is the B at the right edge, so I've got my 2 amps. This time my length, the direction matches the current, it flows up, so it's going to be in the positive J direction. That's crossed with the magnetic field at the right edge of the loop. That was 1 times 10 to the minus 3 Teslas K hat. That gives us 0.8 times 10 to the minus 4 J cross K, sorry, which is I. Units are newtons. So the force on the right edge of the loop is in the opposite direction. It's smaller, so I'll draw it a little bit smaller. Any questions? And then you could have got the direction there with the right-hand rule as well if you wish. So I cross B gives our force pointing towards the right. Okay, part C, find the net force on the loop. So our net force will be the force on the left plus the force on the right plus the force on the top plus the force on the bottom. And those are all vectors. Force on top and bottom, with the symmetry of the problem, those forces are going to be equal and opposite. Okay, so they're the same length, they're in the same spot. The direction runs in opposite directions, so they'll have the same size force in opposite directions. So top and bottom, those are going to sum to 0. So then we've got the left and right stuff that we have to add up. Minus 1.60 times 10 to the minus 4 I hat newtons, plus 0.8 times 10 to the minus 4 I hat newtons. The net force on the loop is negative 0.8 times 10 to the minus 4 newtons in the I hat So overall, the force to the left is stronger than the force to the right, so the net force will be to the left. Okay, next question, find the magnetic moment of the loop. So here we use magnetic moment. It's the number of loops times the current of the loop times the area of the loop. So we're just going to put in the numbers that we know. The number of turns is 1. The current through the loop is 2 amps. The area of the loop is the length times the width. The length was 4 centimeters times the width, which was 1 centimeter. The direction, here we have to remember how we find direction of magnetic moment. You make a circle with your fingers that match your current. Your stuck out thumb is your magnetic moment. So your stuck out thumb points out, so that's alpha in the K direction. So our magnetic moment is 8 times 10 to the minus 4 amps times meters squared. So there's our magnetic moment. Part E, find the net torque on the loop. So if we want to find torque, we remember that that's mu cross B. Our magnetic moment we found is out of the page. Our magnetic field is not constant. It's stronger here than it is here. But regardless of the strength, it does always point out of the page. So I don't want to put in a number for my B just yet, but I will say it points out of the page. So if I'm taking the cross product of two parallel vectors, that means that the net torque is 0. Okay, so yeah. So mu cross B gives us 0 here. Part F, if the loop is free to move, what would happen to it? So what do we think would happen to it? We've got a big force to the left, we've got a small force to the right, and we have no torque. This thing's going to be pulled to the left, right? So the net force is to the left, it will be pulled left. Pulled left, and then I'll add no rotation. And then part G, this is what's going to pull in the induction stuff. If we turn off current I1, what happens? So let's think about what would happen if we turned off our current I1. So this is going to be our Faraday's law of induction. So part G, turn off I1. So we're starting with a magnetic field out of the page. If we turn off the current, we turn off the field. So if we're turning off the field, our magnetic field out of the page decreases. And in fact, it will decrease to 0. If the magnetic field out of the page decreases, what will the induced magnetic field be? Got to be out of the page. We don't want it to decrease. We want it to stay the same. So we will induce B out of page to oppose that change. So we don't want it to decrease. We want it to stay the same. If we induce a magnetic field out of the page, there's our B induced. The direction of the induced current is going to come around counterclockwise. So I induced counterclockwise. So if we had this thing hooked up to an ammeter, we've already got an external battery on it, putting a current I2 through it. We're inducing a current in the same direction as I2, counterclockwise. You can see that the total current would increase. So if you had this set up in your lab and you switched off that magnetic field, your ammeter on this loop would show a sudden jump. And as soon as the field stabilized, the current would go back to just reading I2. Okay, questions? Okay, let's do another one that will be less equation, mathy, more conceptual. Okay, a metal bar moves through a magnetic field. The B is represented by dots, so that means out of the page. What are the induced charges on the bar? So after it's been moving through here for a while, what do you think happens to the charges? I will give you some time to think about it. Okay, anybody want to commit to what they think the answer is? Nobody wants to say. So if you don't want to say, then I'm just going to work through the process. So our wire has positive and negative charges. So that's our conducting bar. It's moving in a magnetic field, so it feels magnetic forces. We'll apply our right-hand rule. So we know that the force is QV cross B. So I'll think about a positive charge. My V is this way, my B is out of the page, my force is this way. So that's my force on a positive charge. My force on a negative charge is opposite. That means my pluses are going to move over here and my negatives are going to move over here. So the answer to the question was B. So if you got that correct on your notes, you can give yourself a star. I think we should do one more example before we clue up the chapter, but I'm not sure that we have time to get started on it now. So this is the chapter we'll do at the start of the class on Monday. You probably should be able to do this on your own already, so I would suggest if you want to give yourself a little test on how ready you are for the final, why don't you try this before class on Monday? Yeah, and then we'll go through it in class. So we'll quit there for today.